Dr. K. Raghuram Mohan Reddy. Today's topic is applications of electron beam machining of the course Unconventional Machining Process. This is the course learning outcome of the today's topic. Understand the applications of electron beam machining. So at the end of this session, student will be able to understand the applications of electron beam machining. Okay, right. Under non-traditional machining processes, we have three main categories: mechanical, thermal, chemical and electrochemical. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. Under chemical and electrochemical, chemical milling, plasma chemical milling, electrochemical milling. Under thermal category, electro discharge machining, electro beam machining, laser beam machining, ion beam machining, plasma beam machining. Now we are in electron beam machining. Today we are discussing the applications of electron beam machining, which is under the category of thermal non-traditional machining process. So here we are discussing the applications of electron beam machining. Right. So before we discuss the applications, let us discuss the factors affecting the performance of EBM. Subsequently, we discuss the applications of electron beam machining. Right. Workpiece material properties such as boiling point and thermal conductivity play a significant role in determining how readily they can be machined. So here the machining is the function of two main things. One is boiling point, the other one is thermal conductivity of the workpiece material. Right. Next, other thermal properties such as electrical conductivity are considered as additional factors. Okay, so the first one is boiling point and thermal conductivity, and the second one is electrical conductivity. These two will play important role in performance of electron beam machining. Right, these are the parameters affecting EBM performance in detail. Okay, so here electron beam machining, under this removal rate, surface quality, accuracy, these are the main outputs from this electron beam machining. Okay, these are the different parameters which influence the performance of this electron beam machining in removal rate, surface quality and accuracy. Okay, right. Now let us see the working material. Okay, under this thermal properties, thickness, ceramic and superalloy. These are the different working materials that can be considered for the electron beam machining. Okay, right. Next, emission current, voltage, cathode. Okay, power density, current, voltage, beam cross section, EBM pulse, duration, energy, frequency, acceleration, voltage. These are the various parameters associated to EBM pulse. Regarding time, removal and pulse, frequency. Okay, so these are the various parameters affecting the electron beam machining performance. Right. Now let us come to applications of electron beam machining. Okay, these are the applications of electron beam machining: drilling, perforation of thin sheets, slotting, integrated circuit fabrication. Okay, drilling, perforation of thin sheets, slotting, integrated circuit fabrication. So these four are the important applications of electron beam machining. So along with these, some other applications are also there, but these four are very much important applications of electron beam machining. Right. Now let us discuss the first one, drilling. So here various researchers and authors have described and uh, expected these are the important outcomes in the research. Right. First one, Steigerwald and Mayer during 1967 considered that for successful application, improved reproducibility, greater working speeds, and deeper holes of accurately controlled shapes are all needed. Okay, so here during 1967, Steigerwald and Mayer discussed the improved reproducibility, greater working speeds, and deeper holes of accurately controlled shapes are all needed. Okay, right. Right. During 1983, Bohme discussed drilling applications with an electron beam machining fitted with a system for numerically controlled NC. Okay, so here electron beam machining is connected with numerically controlled equipment. Okay, regarding beam power, focus and pulse duration, and mechanical motion. Okay, just I wanted to reiterate here. Bohme during 1983 discussed drilling applications with an electron beam machining fitted with a numerically controlled system, okay, to control the beam power, focus and pulse duration, and mechanical motion. So here electron beam machining is equipped with numerically controlled setup to control the beam power, focus and pulse duration, and mechanical motion. Okay, right. Next, regarding hole shapes. Okay, so different shapes of holes like cylindrical, conical, and barrel shaped holes of various diameters can be drilled with consistent accuracy at rates of several thousand holes per second. Okay, see, several thousand holes per second. So that is the efficacy of the electron beam machine. And at the same time, the accuracy is consistent, and we can obtain various diameters of holes. Okay, and the shapes may be cylindrical, conical, and barrel shape. Okay, so this is an important feature of the electron beam machining in order to have different diameters of holes and the accuracy and the number of holes in less time. Okay, that is several thousand holes per second. You can imagine uh, the efficiency and the productivity of the electron beam machining and its performance, right? And it makes the holes with consistent accuracy, and we can have different or various diameters of holes. Okay, right. And also holes at an inclination angle of about 15 degrees are also possible. Okay, so here holes can be perfectly on the surface, or we can make holes with an angle 15 degrees. Okay, again let us see some more important points by Bohme. Bohme during 1983 claimed that the largest diameter would be 1.55 mm. Okay, the depth of holes can be accurately drilled by EBM or 10 mm. Up to 10 mm depth of holes can be drilled by electron beam machining. Okay, so here the largest diameter can be 1.55 mm and the depth can be 1.55 mm and the depth can be 10 mm. Okay, right. Aspect depth to diameter ratio is normally in the range of 1 point, sorry, 1 is to 1 to 1 is to 15. Okay, what is this? Aspect depth to diameter ratio. Okay, aspect depth to diameter ratio will be in the range of 1 is to 1 to 1 is to 15 in the normal conditions. Okay, for deeper holes, the range, that means aspect depth to diameter ratio, will be 2.5 to 7.5 mm. Okay, right. Once again, I reiterate this aspect depth to diameter ratio for normal condition and for deeper holes. Okay, so normally the ratio will be 1 is to 1 to 1 is to 15, and for deeper holes it will be 2.5 to 7.5 mm. What is this one? Aspect depth to diameter ratio. Okay, aspect depth to diameter ratio. Okay, so this one for normal condition, this is for deeper holes. Okay, right. Hope you understand the aspect depth to diameter ratio normally and for deeper holes. Okay, right. Right. During 1967, Steigerwald and Mayer emphasized the need for a stable power supply that can emit the required groups of pulses, and that for a well controlled beam of closely defined diameter, this is one, for a well controlled beam of closely defined diameter. Second one, the angle of aperture has a strong bearing on the shape of the hole produced. Okay, so during 1967, Steigerwald and Mayer concluded or described the stable power supply that can emit the required groups of pulses, and that for a well-controlled beam of closely defined diameter, and the angle of aperture has a strong bearing on the shape of the hole produced. Okay, so these two are the important parameters of this machine. Right, here holes of about 19 were produced. Okay, Steigerwald and Mayer concluded that holes of about 19 were produced. Okay, that means diameter of the holes. Right. Another researcher drew during the 1976 showed electron beam drilled holes in a superalloy turbine blade at an angle of 60 to 90 degrees. Okay, so earlier we have seen that 15 degrees of holes can be made. Okay, now in the year 1976, Drew experimented and concluded and facilitated to make the holes with an angle 60 to 90 degrees on a superalloy turbine blade. Okay, this is an important application for the turbines. Right. Now drilling over. Now the second one, perforation of thin sheets. Okay, for perforation of thin sheets, we have to see the economical acceptance. Okay, right. For perforation by EBM to be economically acceptable, 10 power 4 to 10 power 5 holes per second have to be produced. See, imagine 10 power 4 to 10 power 5 means 10,000 to 1 lakh holes per second on thin sheets. Okay, perforation of thin sheets. Okay, right. Thus, single pulses lasting only a few microseconds are needed. Okay, within few microseconds we can produce so many holes. Here per second 10,000 to 1 lakh holes can be produced. Okay, per second. You see, not minute, per second we can produce 10,000 to 1 lakh holes. Okay, right. In some applications, the sheet or foil is stretched on a rotating drum. So here, sometimes we can stretch the sheet on a rotating drum, which is simultaneously shifted in the direction of its axis. Okay, right. Rows of perforations following helical line are thereby produced. Okay, so here when we stretch the sheet on a rotating drum, okay, what will happen? Helical line will be produced. Okay, in a row wise. Okay, so here rows of perforations following a helical line are thereby produced. Okay, right. So here what is happening? The sheet or foil is stretched on a rotating drum. Okay, right. Right. Manipulators capable of linear and rotating movements in 4-axis are used for electron beam machining perforation of jet engine components. So here 4-axis robotic setup. Okay, manipulators means the robotic setup capable of linear and rotating movements in 4-axis are used for electron beam machining perforation of jet engine components. Okay, right. This is important application for perforation of sheets. Right. Foil made of a synthetic material has been perforated with 620 holes per square millimeter for filter application at a rate of 1 hole every 10 microsecond. Okay, so here 620 holes per square meter. Sorry, square millimeter. Square millimeter means one millimeter means just one dot. Okay, so within that, okay, 1 square millimeter means almost just a dot. Okay, here 620 holes. Can you imagine? Okay, foil made of a synthetic material has been perforated with 620 holes per square millimeter for filter application. So here the application is filtering. Okay, at a rate of 1 hole every 10 microseconds. Okay, so in 10 microseconds 1 hole will be producing. Okay, right. EBM perforation can be applied to the production of filters and masks of color television tubes. Okay, so for color TV tubes, filters and masks are producing with this EBM perforation. Okay, right. Other applications for perforation lie in sieve manufacture for sound insulation and in glass fiber production. Right. Other applications for perforation lie in sieve manufacture for sound insulation and in glass fiber production. Right. Other applications for perforation lie in sieve manufacture for sound insulation and in glass fiber production. Okay, right. Next one, slotting. Third one, drilling over perforation of thin sheets over. Now slotting. Right. Rectangular slots of 0.2 by 6.35 mm in 1.57 mm thick stainless steel plates are produced in 5 minutes using 140 kV, 120 microampere. Okay, so this is voltage, this is current. Okay, this is time. Okay, and a pulse width of 80 microseconds and a frequency of 50H. Okay, so here rectangular slotting. Okay, rectangular slots of 0.2 by 6.35 mm in 1.57 mm thick. Okay, so here the thickness is 1.57. This is thickness. Okay, and this one with its 0.2 mm. This one is 6.35 mm. Okay, stainless steel plates are produced in 5 minutes using 140 kilovolts with 120 microamperes with a pulse width of 80 microseconds and a frequency of 50 Hz. Okay, so here the slot is with 0.2 mm. This is 6.35 mm slot, and the slot thickness is 1.57 mm. Okay, okay, right. Just this is exaggerated the same. Okay, right. This is about slotting. Again, we'll see the other things. The rate of slotting depends on the workpiece thickness. Okay, the rate of slotting depends on the workpiece thickness. So here the rate of slotting is the function of the workpiece thickness. Okay, okay. Here the rate of slotting depends on the workpiece thickness. Okay, right. In this regard, 0.05 mm thick stainless steel was cut at a rate of 100 meters per minute. Okay, here 0.05 mm thick stainless steel was cut at a rate of 100 meters per minute. Okay, so here the thickness is 0.05 mm. Okay, if the thickness is 0.05 mm, it will cut 100 meters length in 1 minute, that is in 60 seconds. Okay, so while 0.18 mm thick stainless steel was cut at 50 meters per minute using similar machining conditions. Okay, so here when the thickness is 0.05 mm, it can cut 100 meters per minute. But if we increase the thickness from 0.05 to 0.18 mm, okay, the rate is 50 meters per minute. Okay, the slotting rate for this stainless steel is 50 meters per minute. Okay, for the same machining conditions. Right. Now we'll see integrated circuit fabrication. These three over. Okay, now we are discussing integrated circuit application. Okay, right. In the year 1967, Benny and Chapney, okay, Benny and Champney drew the attention to use of electron beam technology in scribing thin film circuits for the electronic industry. Okay, so where the integrated circuit fabrication has come up with this application. Okay, a detailed account for the manufacture of integrated circuits ICs has been presented by U. Teller during 1994 with the complete application performance. Okay, right. The beam is positioned accurately by means of deflection coils at the location where a pattern is to be written by exposing a film of electron resist coated on either a chrome mask blank or wafer for the production of the lithographic definition required. Okay, so here the beam is positioned accurately by means of deflection coils. Okay, so here the beam is accurately positioned by deflection coils at the location where a pattern is to be written. Okay, by exposing a film of electron resistant coated on either a chrome mask blank or wafer for the production of lithographic definition is required. Okay, so an electron beam of energy about 10 to 20 kilowatts can either break the bonds between the polymer molecules or cause cross-linking the polymers. Okay, so what will happen? Either break the bonds between the polymer molecules or cause cross-linking in the polymers. Okay, at what range? At 10 to 20 kilowatts range. The electron beam. Right. With the onset of either these conditions, the solubility changes when the resist film is immersed in the developer, usually the solvent for the resist. Okay, so here usually a solvent for the resist. Because of the difference in solubility between the original and exposed resist polymers, a differential material removal occurs. Okay, so because of the difference in solubility between the original and exposed resist polymers, a differential material removal occurs. Okay, right. Right, a fine pattern of polymer is thus obtained, which is used as an active mask to avoid unwanted etching of the integrated circuit mask. Okay, a fine pattern of polymer is thus obtained, which is used as an active mask to avoid unwanted etching of the integrated circuit mask. Okay, right. Pattern generation can be carried out by a vector scan. Okay, by using vector scan, we can generate pattern system. Right. The electron beam is deflected only to the locations at which the electron resist is to be exposed. Okay, so here the electron beam is deflected only to the locations at which the electron resist to be exposed. Okay, as soon as the deflection system completes the positioning of the beam at the required place, the electron beam action is started. Okay, right. right? With raster scan method described by Megoff during 1988, the chip pattern is divided into subfields. Okay, so here the chip pattern is coming to the effect. The electron beam in a raster like that employed with the television scans each subfield. Okay, the electron beam is turned on and off along each raster line as needed. Okay, so here the electron beam is turned on and off along each raster line as needed. Okay, this is what we have been seeing in the televisions. The required pattern is fully formed by the combined effects of electron beam exposure and subsequent resist development. Okay, one is electron beam exposure, the other one is the resist. Okay, so here the combined effects of electron beam exposure and subsequent resist development. Okay, so here the pattern is fully formed with the combined effect. Right, here the figure 3 shows a typical application where electron beam machining is used for a miniature electron hybrid circuit engravement with 40 micrometers wide trace. Okay, so here hybrid circuit engraved with 40 micrometers traces at speeds greater than or equal to 5 meters per second. Okay, so this is the architecture of this circuit. Okay, right. Direct wafer processing by EBM is necessary for feature sizes below 1 or 2 microns. Okay, so here direct wafer processing by EBM is necessary for feature sizes below 1 or 2 microns. Okay, next line width as well as several hundred of an angstrom can also be written with electron beam techniques at speeds as high as 20 megahertz. Okay, so here line width as small as several hundred of an angstrom can also be written with electron beam techniques at speeds as high as 20 megahertz. Right. Direct wafer processing electron beam systems are capable of producing 20 wafers per hour. Okay, so with this we have been completed almost all the applications. Now these are the references. Okay, right. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.